And we're started. Welcome. Lecture 5. Today we're going to make a major step in our study of astrophysics, moving from talking about stars from the outside and how we can see them only on the surface or characterizing the surface, and starting to understand stars on the inside, what happens inside stars, how they are built, and what makes them tick, or what actually powers them, what makes them run. And answering the question, in some sense, the most important or ultimate question, what are stars to begin with? So I'm assuming today everyone in these days have grown up with some sort of answer. Okay, so as Pumba put it, and as we all know today, stars are basically balls of gas burning millions of miles away. But that, of course, was not always the answer. And the question of how do we know that, and what exactly do we mean by burning, is a big one. And that's the question that we'll try to answer today. So to put the modern definition of a star in one well-organized place, a star is a celestial body, millions of miles away, basically puts it far outside the Earth. And other than our own sun, which is rather close by, most stars are, as we know, parsecs away, light years away, kiloparsecs and more, very, very far away from us in the sky. A star is held together by self-gravity. So its own huge mass creates gravity that holds it together. It's not something like a big magnet or a big electric charge. It has, on those size scales, gravity is the thing that holds it together. And we've already discussed earlier when we mentioned asteroids, for example, that the bigger the object is and the more massive it is, the stronger the gravity. And typically, when we're getting to planet size and star size, they tend to be round or spherically symmetric, mostly spherically symmetric, almost completely symmetric, because gravity is the thing that holds it together, and gravity kind of works symmetrically to pull it into a spherical shape or to create a very strong energetic impediment for non-homogeneity or non-isotropies. The difference between a star and a planet is the energy production. So while a planet is typically small and cold, and it can also be a ball of gas, like some planets in our solar system, the gas giants, Jupiter, Saturn, Uranus, and Neptune, they are gassy, as opposed to our own planet, which is Earth-like, terrestrial. It's made of solid rock, basically, mostly. The Earth, Mars, Venus, Mercury, and some would count Pluto. The rocky planets, which are smaller. The bigger planets have more mass, and when mass is large enough and gravity is strong enough, it can hold gas around it, not to disperse into space. So we have planets which can also be gassy, but they'll be cold, and in particular, they won't undergo nuclear reactions or nuclear fusion, which it will not be the source of energy in gassy planets, as opposed to the stars, which are large enough balls of gas to be dense enough and hot enough to ignite nuclear fusion and undergo various processes of nuclear reactions powering the star. These stars are not just like hydrogen bombs or atomic bombs on Earth. They're in equilibrium. They're not just something that happens accidentally or momentarily. A star is defined by being in equilibrium. So it's basically balancing out the different forces and processes which work or operate inside the star. And while we have gravity pulling the star inwards to prevent it from collapsing, we have the pressure coming from the nuclear energy production, which heats the gas and creates pressure, pushing outwards against gravity. And it's this equilibrium which keeps stars stable and stationary for, as we will see, a very, very long time, billions of years if we're talking about the main sequence for stars like our sun. So we have kind of an overview here on the right of some of the topics that we mentioned that we'll be covering more in today's class, and in next week. We'll continue talking about stellar structure next week as well. This is a model of our sun, or more exactly, the upper two the upper two quadrants, the upper half, is models or illustrations of our sun. And on the bottom, we have two real images of our sun taken at different wavelengths. On the left, we can see kind of a picture of the sun with a few effects we'll be discussing, like sunspots, which I think we'll cover maybe in 1 or 2 weeks. The darker patches are sunspots. We can also see an effect of limb darkening. That is that the sun becomes a bit dimmer and darker towards the edge. If you look at it with your eyes, you'll see just a big bright circle of light. But if you actually put on filters and tune it out a bit, you can actually see that there's a gradation. There's a differential in light between the middle and the out, and it gets dimmer towards the edge. That's called limb darkening. We'll talk about that as well. On the right, we see an image in a different wavelength, which showed us a lot more solar activity. We can see some of these kind of texture of the sun, which we'll talk about next week, is coming from convection cells and this bubbling of the surface of the sun. And we can also see ejections from the sun, solar flares, coronal mass ejections, solar winds, some of the solar corona, other types of effects that come out of the sun, or that we can see if we observe a star like the sun. On top, we have kind of an analysis of what goes on internally, which again is something that we'll start talking about today, showing different layers of the sun. Here on top, on the left, we see the solar core, which is approximately where the nuclear reactions take place, followed by the stellar interior divided into two parts. A part that's governed by radiation. Energy transfer there is mostly radiation mediated. Further on the outside towards the surface, we have convection dominated regions. So we have blobs of matter floating around, kind of like the atmosphere of the Earth, or like a kettle that you boil. We have transfer of large blobs of matter. And this convection in the sun reaches the surface, and that's what we actually see. If we look at the solar surface close enough, we can see traces of this convection, or the results of this convection. On the right, we see a model or an illustration of the temperature changing within the sun. And here the temperature is coded in by darkness of color. The core itself is hottest, and it gets colder and colder as we go outside. And this also is related to the limb darkening I mentioned before, which we'll talk about and calculate using the opacities of the internals of the sun. So again, as we can see, even in this very preliminary cartoon, basically, a star like our sun is a very complicated object. A lot of stuff are going on inside, and we'll try to take the next couple of classes slowly to cover all of these processes from the nuclear energy production by fusing hydrogen to helium on the main sequence. This process is a thermonuclear process, so it's the temperature that causes the ignition of hydrogen, which means it happens in the core, where it's the hottest in the sun. It must be hot enough to sustain nuclear fusion, otherwise we can't have a main sequence star. It has to be stable and go on for a very, very long time. And at the end, when eventually every star will run out of fuel, it will go into one of the decay modes and one of the aging and retirement stages of a star's life. And we'll cover those as well in 2 weeks when we talk about stellar evolution and stellar remnants. But this is the overview of what a star is. It's basically a big ball of gas that gets denser and denser towards the center, therefore hotter and hotter towards the center, until close enough to the center in the core, it stably burns hydrogen into helium for a very, very long time. Any questions so far?
כן, באיזה מצב צבירה, כאילו מה נמצא בתוך הכוכב הזה? זה גז, זה נוזל, כאילו מה זה?
So the state of matter is typically plasma. For very cold stars like M-type stars, which are, if you remember the right edge of the AGR diagram, the outer part of the atmosphere can actually be cold enough for atoms not to be ionized, and then it's just gas, and you can even have some simple molecules floating around in the atmosphere. So the outer part of the atmosphere can be gas, but very quickly when you go into the star, and for stars like our sun, it starts even at the very edge. There's no pure gassy part. The molecules get ripped apart by the by the temperature. Atoms themselves get ripped apart and ionized electrons get pulled out. So the most accurate description of the state of matter is plasma. But for our intents and purposes, we can think of a plasma as a gas, or rather as a mixture of gases, where some of the gases are ions, positive ions, and some of the gases are just floating electrons. And as we discussed last week, a star is generally neutral, or at least if there is any surplus charge, it's insignificant in comparison to the mass of the star and what actually goes on in the star. So we can just think of it as a mixture of gases, mostly electrons and ions, and the ions themselves are mostly hydrogen. About 90% of the atoms in a star like ours will be hydrogen, and the other will be 9-point-something% helium atoms and trace amounts of all the rest. Some carbon, some oxygen, some other metallic elements. But all of these atoms will be ionized either once or more. So it might have, an oxygen might have a few electrons clinging to the inner shells, but will still be mostly ionized. So we'll have a large amount of electrons floating around, and it's basically a plasma.
אוקיי, אפשר עוד שאלה? בליבה של הכוכב יש שם משהו מוצק? כאילו זה...
No. It's very, very dense, but we can't think of it as as a regular solid, as something like it's not a diamond, it's not something that you can think of as rocky. It will be very, very dense, but it will not be organized as a solid. The temperature is much, much higher. We'll get to the temperature in the middle of the center of our sun is about 13 or 14 or maybe even 15 million degrees Kelvin. So that's way above the melting temperature, and of course even the gas temperature and ionization temperature of any actual solid that we know. Again, because it's not composed of just stable molecules, everything is ions and everything is plasma. It's a very, very dense, thick, hot plasma. Okay. So we talked about these stars being stable and living for a very long time, and that brings us to the question of how do we actually estimate time durations and timescales for a star's life? How long does a star live for? How long can we measure, and how can we understand the durations of a star's lifetime? And we start by measuring, or our first guess will be measuring the lifetime of our own planet Earth. So this is actually a rather recent field or methodology in a historical context. Up until about 200 years ago, there were no actual good answers to the question of how long the stars live and even how long the Earth has lived for. We basically had two types of answers. We had the ancient Greek answers following the school of Aristotle, saying that the universe was eternal, posing this as a completely philosophical position, not motivated by any physics. The Greeks of Aristotle's school believed in symmetries and in that things that are symmetric have to be perfect and eternal, and obviously cannot have a beginning or an end, because that would imply some blemish or some problem on their being perfect. The opposite answer was the answer that came from Jewish and Christian religious sources, basically following the story of Genesis, saying that there was a beginning to the universe. We don't know necessarily about an ending. Bible is iffish on that part, but at least regarding the beginning, it was apparently considered well documented in Genesis, and people calculated how long ago it was based on various counts of events in the Bible. The two traditional numbers that were accepted were the Jewish dating, which we use to this day. I think we're now in year 5,780 something, 81 maybe, to the creation of the earth according to Jewish sources. Christian sources adapted a slightly different counting. They were basically off by about 250 years from the Jewish numbers. But that's what people thought was the age of the earth. So about 6,000 years, or between 5,000 to 6,000 years. Newton, who was generally actually a rather decent mathematician and physicist, also delved in this kind of analysis of religious texts for dating periods. And he actually predicted the earth and the universe in general should end about 40 years from now, in the year 2060. And this was basically what people did up until the 19th century, because there were no actual sources of evidence to consider that could actually tell us how old our Earth was or how old stars were. So guesswork and text analysis were basically all that they had. This changed slowly, but in a very promising direction in the 19th century. And it's interesting to say that both of the new answers from the 19th century about the age of the Earth as a planet, and from that we can infer the age of the sun and kind of understand the scale of stellar lifetimes, were not given by astrophysicists. Actually, they were not given by physicists at all. They were given by William Smith, who was nicknamed William Strata Smith. Strata is a name, is layer in English. Who was a geologist, basically one of the founders of the field of geology, and by Charles Darwin, who I'm sure you've heard about in biological contexts and in his theory of evolution. What William Strata Smith noticed as a geologist and a geographer was that there was a structure to the Earth itself. He studied England, also Wales and parts of Scotland, and he mapped different and documented the types of rocks that he saw. And he noticed that there are features in rocks. If you dig or look at a coastline or look at some place where a mountainside is exposed, you can see this layering phenomena, which is very familiar to anyone who's gone traveling, even in Israel in the south or elsewhere. This, I think, is a canyon in the United States. It very clearly shows layers upon layers of land, which you can distinguish from each other. And you can distinguish by color, by chemical composition, and what he noticed first, by the different types of fossils that you find in different layers of soil. Trying to realize where this layering effect comes from led him to study the rate at which new soil was deposited on top of old soil. And you can do this from analyzing rivers depositing matter, erosion of different types of land over a very long period of time due to wind and water effects, and other studies. And these led him to realize that the time scales are typically very, very slow, And so to develop features such as these, and to kind of find the depth of dirt and earth and soil in the different layering that he discovered, he came up with numbers indicating hundreds of millions of years. As again, this is just a low bound on the age of the Earth, hence a lower bound on the age of our solar system, because all of these earth and wind, wind and water, for them to actually flow, you would need the sun as we know it and an ecological system as we know it. And extending those calculations backwards in time would give you hundreds of millions of years at the least as an age for the Earth. Again, this is the time where Isaac Newton's estimate was 6,000 years. And now comes this geologist and gives us a number that's 100,000 times longer, hundreds of millions of years longer than any number that duration of time anyone could actually grapple with before, much longer than human history by orders of magnitude. Around the same time, Charles Darwin, of course, did his biological experiments and observations, cataloging different types of birds in the Galapagos Islands and other type of plant and animal life, documenting them for tens of years, and going over his observations back in England and classifying them and discussing with other people, and came out with this idea that biological species were not all created at once the way we know them today, but that they actually show in evolution. They develop with time, and the process that causes them to develop with time or to evolve is a random process. You can think of it as a version of a random walk or a diffusion process where traits appear at random and disappear at random, but the main feature is that they are not copied at random. So a random accident which changes a feature of an animal, which causes that animal to be better suited to its environment and have better survivability and produce more offspring, will spread in the next generation, while random perturbations which operate in different directions will either have no effect or even hinder the survivability of that animal. And so most mutations will die out and cause extinction of themselves, of those mutations. Only those mutations which are beneficial will be selected for naturally by environmental pressure and will spread out throughout the environment and the population and overcome and become more prominent. Because this process is random and the time scale is basically from generation to generation, and you have to wait until a mutation appears, wait for one of those mutations to actually be beneficial, and then be selected for and start spreading, this again creates a very, very long process. It doesn't happen fast. Today we can see evolution in a lab with bacteria. We can cause bacteria to develop, for example, resistivity to antibiotics, and we can see on an hour-to-hour scale, which is about the reproduction generation time for bacteria, we can see different types of populations evolving antibiotics resistivity. But if you look at humans or monkeys or birds, then the time scale is much longer, and it will take a very, very long time. And so Charles Darwin also says, I've measured this evolution of species by natural selection as a random process, not guided. It takes a very long time, and came up as well with numbers indicating hundreds of millions of years as being required to actually evolve species from basic simple ones to the complex ones that we know today. And interestingly, the geologist numbers and the biological numbers were along the same orders of magnitude. They didn't exactly fit. At some point, they started feeding each other information, because obviously you can see these different types of fossils along different evolutionary stages appear in the same geological strata of Earth. So you can kind of start dating and timing the evolution of species along with and calibrated against geological phenomena. So this was very useful. And the numbers again came up to orders of magnitude of hundreds of millions of years, or order of 1 billion years, as again, just a lower bound on the age of the Earth, because that's the time where the Earth should have been at least stable enough to sustain an uninterrupted line of life up from the early one cell bacteria, basically, to what we know today. And with all this information coming in, what the physicists had to say was that they didn't believe any of it. No physics that they knew could sustain the Earth for so long, or sustain a star for so long. And physicists basically ignored these biologists and the geologists as people who are not real scientists, while in fact these biologists and geologists are the ones who had the right answer, and physicists didn't even know what was coming. Any questions so far? Okay. So these kind of suggestions by scientists outside of physics did cause physicists to at least need to give a response, or to give our own answer of how we could understand a lifetime of a star, or try to figure out how to measure or how to give at least upper or lower bounds. And the answer, that the modern physical answer, not the Newtonian text analysis, but something more modern, was that a star produces energy. That is something, as physicists, we can measure. We talked about it last week and the week before that. We can measure the luminosity, the solar constant, how much energy the sun produces arriving at Earth. We can multiply the amount of energy, the flux arriving at Earth, by the distance of the Earth from the sun, an astronomical unit, which also as astrophysicists we have measured. Multiply the radius squared by 4 pi, by the flux, and get the total energy production of the sun. This rather large number, about 4×10⁻26 watts. We also measure the solar mass. We can do that again from Kepler's laws, Newton's laws, by measuring gravity of the sun. And we come up with a number which is about 2 × 10⁻30 kilograms. And now we have the question of, obviously the sun can't just take energy from nowhere. It has to use whatever mass is available in some physical process to produce energy. And the amount of fuel that we have, in some sense, is this mass of the sun. We have to sustain a luminosity of 4 × 10⁻26 watts. And let's see how long we can burn or use our fuel, not necessarily even burn, but how long can we use our fuel until it runs out at the required luminosity. So the first process that scientists considered was the most available and common energy production method in the 19th century, and sadly, still the most common energy production method till this day, which is chemical processes burning things. You take fuel, be it natural gas or oil or coal or wood or anything else, you burn it, and you can measure how much energy this chemical process will produce. And as we discussed, I think 2 weeks ago, typical chemical potentials are approximately 1 electron volt, order of magnitude of an electron volt, which of course is why we measure chemical potentials in a lab from batteries in volts, because when you produce electricity from chemical reactions, a volt is the typical potential that you get. Typically 1 or more electrons, but a small finite number of electrons will be involved in each of these reactions. So if you have a few electrons times order of an electron volt, order of a volt of potential, you get an energy per reaction of about order of an electron volt. And this turns out to be a ridiculously low number for the sun. It gives you a lifetime if all the sun were doing was burning chemical fuel of a few tens of thousands of years, which is not terrible. much more than, again, the Newtonian or religious supposition of old, but nowhere near long enough to sustain what Darwin and Smith were claiming. So the evidence on the Earth was suggesting hundreds of millions of years. Chemical processes cannot sustain more than a few tens of thousands. The chief opponent of this longevity of the Earth argument, that is the physicist most prominent for objecting to the Earth living for a long time and arguing for a short lifespan, was Lord Kelvin, the scientist called Thomson, or given the title Lord Kelvin. You know him mostly from the degree, Kelvin, the scale named after him, for his works in thermodynamics. Some of you might also know him from a lot of works in hydrodynamics, instabilities and things like that. Leading scientist in England at the end of the 19th century, given a lordship, and he claimed that the Earth didn't live for a long time. The sun could not live for a long time. Tens of thousands of years was basically what he offered. But he suggested that the sun could actually produce energy by contracting and releasing gravitational energy. And we'll talk about that in a moment a little more. That also doesn't give much more than tens of thousands of years. The first person to actually realize that something else might be causing it, something more effective, which could produce more energy per mass, therefore give a longer lifetime at the same amount of mass, the same budget of fuel, was Ernst Rutherford, whom you know from quantum mechanics, from the Rutherford model. He realized very early on in 1904 that a lot of energy can be released from nuclear processes. In particular, the nuclear process he was familiar with, one of the first one discovered, was nuclear fission. Fission is something that happens when a heavy nucleus breaks apart into two smaller ones and releases some radioactive radiation, which could be alpha particles, that is protons and neutrons bound together in a helium nucleus, or alpha or beta particles, which are electrons, or gamma radiation, basically photons of very high energy. And the most common of these, or the most familiar of these today, is of course uranium breaking apart, releasing neutrons, and this is what powers atomic bombs and atomic power plants. But there were other fission processes which were known. They can happen spontaneously. Uranium has a half-life of billions of years, as you might have seen in the homework exercise. So if a half-life is billions of years, that means theoretically the process can take order of billions of years until the last uranium nucleus breaks apart spontaneously. Also, you can produce a lot more energy per reaction, because nuclear reactions are typically on the order of a mega electron volt, so about 1 million times more energy per reaction than chemical reactions, which means you can bump up your estimate of tens of thousands of years to tens of billions of years, and now you're consistent with the lower bounds produced by biologists and geologists. So famously, Ernst Rutherford gave a talk in England, and Kelvin was in the audience, and Rutherford was reviewing the claims about the age of the Earth, and Rutherford didn't want to insult Kelvin, so he repeated his arguments and said that all the bounds that we know show that the Earth is actually very, very young, but that's because we have not yet considered nuclear fission as an energy source. And today, of course, we know that nuclear processes are the energy source of the sun, but it's not fission. There's actually very little uranium in the sun, and it's not produced in the sun even. Nuclear fusion, of course, is what powers stars, as we said. Fusion is taking two small nuclei, putting them together to form a heavier one. Fission is taking a already large nucleus and breaking it apart. Questions so far?
How do we know that we can rule out fission and know it's fusion, not fission?
Well, the first way is to see that there's just not enough uranium in the sun. It doesn't contain heavy elements. In a few slides, we'll also see the crushing proof, which is that nuclear fusion in some critical stage produces neutrinos using the weak interactions. And today we have succeeded in measuring these neutrinos from the sun. So we have actual direct evidence of fusion. But at the time, about 100 years ago, actually just under 100 years ago was when Eddington proposed fusion as the mechanism. The main evidence for that, or the main reasons for that, were just the chemical composition. The sun is, as we said, 90% of the atoms are hydrogen and about 10% helium. It's natural to assume that the processes governing it will be involving hydrogen and helium and not uranium, which we don't even have naturally appearing in the sun.
Okay, thank you.
Okay. But let's go first through Kelvin's argument to see kind of what people tried before and also understand an important physical result regarding gravity and general potentials called the Virial theorem. Has anyone here encountered the Virial theorem before? In any context?
Yes.
Yes, good. Excellent. So the Virial theorem relates the kinetic energy of a system to the potential energy of the system. And it has a lot of assumptions. You can take it in different forms. You can take it from circular motion. You can take it on average in a multi-particle system and have some statistical averaging. But what it basically says is that if you have a simple potential between two particles, which is given by some power law r to the n, then you can convert that potential basically to a force. You can integrate the force with velocity to find work. Work will give you the kinetic energy change. And if you average over all particles, you'll see that energy has to be basically distributed between the potential energy and the kinetic energy. And on average, it means that twice the kinetic energy is equal to n times the average potential energy per particle. You can see this in the simplest case, which is also the most interesting to us, the gravitational case, where n is -1. That is the potential energy. The potential goes like 1 over r. That's a Newtonian potential. And then you have that n equals 1. So this is just a -1 on the right. N is -1. Dividing by 2 means that the kinetic energy is minus half the potential energy. And if you recall a bound system, a system is bound if the total energy is negative. In this case, it would mean that the total energy will be negative. So minus negative will be positive. The kinetic energy will be positive, which is natural. Kinetic energy always has to be positive. And it will be equal to half the total energy, or minus half the total energy. So basically, the potential energy is equal to -2 the kinetic energy. And the total energy, which is the potential, which is negative, plus the kinetic, which is positive, gives you minus half the kinetic energy, or minus half the potential energy. Kind of an order of magnitude calculation for the relation of kinetic to potential energy. But potential will be negative, kinetic will be positive, but kinetic will be half as positive as potential is negative. So the total is still negative, and the system is still bound. It's not a free system. In a star, all of this kinetic energy has to be in the form of particles in the gas moving around. And on average, that's what gives us the heat, right? We can relate the temperature of a gas to the kinetic energy per particle or per degree of freedom. For example, if we consider an ideal gas, and we have our favorite relation, PV equals NKT, relating volume and pressure to temperature and the density or number of particles in the gas. On average, this means that the kinetic energy per particle, which is 1/2 v squared, if you want, you can flip this m to the right side to have mv squared over 2, the kinetic energy of a particle, will be, this is also the equipartition theorem, if you know that one from thermodynamics, 3/2 Boltzmann constant times t. The 3/2 comes from, well, the 3 comes from three-dimensional space, and the half kT is average energy per degree of freedom of a particle in however many dimensions that you have. So in a sense, this is the virial theorem kind of can be related or used with the equipartition theorem to relate the temperature, the velocity, through the velocity, the kinetic energy, through the kinetic energy, the potential energy. What that then means is that because the potential goes like -1/r, if the star shrinks in radius and becomes denser, that means that the potential goes down. You're deeper into the potential well. Being deeper in the potential well means that you're increasing the kinetic energy, right? Because the kinetic energy is half the potential energy, or -1/2 the potential energy. So if the potential energy is more negative, the kinetic energy is more positive, which means basically half of the energy you get from shrinking the star goes into kinetic energy, which goes into heat. It heats the gas in the star. And that's the way you can produce energy this way, kinetic energy, heat energy, and that heat will be radiated away as radiation. You do it by shrinking the star gradually. So Kelvin managed to get an estimate or a suggestion for an estimate for the lifetime of the sun by saying that it's no longer an eternal, constant, stable star. It's changing with time. How does it change? It contracts. It contracts very, very slowly, releasing potential energy into kinetic energy and releasing it as heat and radiation. And this estimate you can do. You can do it quite easily. Get a bound on the lifetime of the sun if you take r from infinity and shrink it to the known radius of the sun today, which is about 700,000 kilometers, and just see how much potential energy was, how far down you went in the potential energy. Well, half of that was released or would have been released as heat, and see what luminosity that produces, and divide that amount of energy produced by the luminosity that you observe, and see how long this process could have been sustained at the current luminosity. And again, you come out to one of these standard physicist numbers from the late 19th century, which are tens of thousands to maybe 100,000 years. That's the order of magnitude of duration for heating a star to the current luminosity by collapse. Any questions so far? Okay, I will say that this calculation, although today we know this is not what powers the sun today, again, the sun is powered by nuclear fusion, which means it can live for much longer. But this process was important in the history of the sun, because today we don't think that stars just pop out of nowhere. They start as even bigger balls of gas, which are cold. Gravity then pulls the stars in. As long as they're cold, the pressure is weak, so it cannot stop the gravitational collapse. And so stars, or protostars, the gaseous regions of space which are not yet burning hydrogen, they're cold, will slowly contract. While they contract, they release potential energy into kinetic energy and into heat. That heats them up until they get hot enough to ignite hydrogen, and then temperature rises a lot, energy production rises a lot, you get pressure to rise a lot, and that pressure stops the further collapse. So stars don't live this way, the way that Lord Kelvin proposed, but stars are born this way. The initial heat required to ignite a star comes from this contraction using, and you can calculate it using the Virial theorem. Okay.
אפשר לשאול? למה
כן.
שהרדיוס
Yes.
יקטן פתאום?
Again?
למה שהרדיוס של השמש יקטן?
Because of gravity. Gravity causes contraction. And the sun is very, very massive. There's a lot of mass. So contraction is very, very, it's a very strong force, the gravitational force causing contraction. And it's stronger than any other force around that can stop it, as long as the gas is cold. When the gas gets hot enough by burning hydrogen, then the temperature rises, the pressure rises, and the pressure will stop further collapse, will stop contraction. So basically the sun today is more or less at the radius it was when it was first ignited. But when it started off, it could have started off as big as the entire solar system or more. And it's an open question whether we as planets formed together with the sun a little earlier, a little later, from the same primordial protostellar disk or matter. But basically the sun itself would have kept contracting until ignition. Okay. On that note, let's take a break until exactly 1 o'clock and then start going deep into nuclear energy production as we understand it today. Okay. So as we said, many different ways of producing energy were ruled out in the turn of the 19th to 20th century, basically by not being able to provide for a long enough duration of energy production to sustain the length of time that the sun has existed for, as inferred from completely non-physical but very scientific and very correct Earth measurements in biology and geology. And this was the case until the final answer was given as fusion of hydrogen into helium by Eddington in 1926. This is a very interesting prediction by Eddington, which of course now we know to have come true and to be correct, because here, it was given before the neutron itself was even discovered. Chadwick discovered the neutron in the early 30s, so people didn't even actually know the composition of helium when Eddington made this prediction. They knew that the mass of a helium nucleus was 4 units of mass, 4 atomic mass units. They knew it was 4 times heavier than an atom or a nucleus of hydrogen, but they knew that the charge was 2, that it had 2 protons, or an electric charge of 2, but they didn't really, no neutron was actually discovered, yet still they realized that the mass has to come from 4 protons or 4 hydrogen atoms to combine together to produce 1 helium atom. And they could kind of start inferring what kind of energy will be produced from that process without being able to reproduce it yet. It took decades until we could reproduce the process. By again looking at this curve here on the right, this plot that we have, showing the average binding energy per nucleon for various elements in the early stages of the periodic table, or isotope table in this case. And you know the average binding energy because Einstein has told us that delta E equals delta mc squared. So whatever excess mass you either have or are missing would have gone into energy. And you can measure the mass of a single hydrogen atom or a single hydrogen nucleus without the electron, which has very little mass. And you find that the hydrogen nucleus or a proton has a mass of about 938 mega electron volt in our favorite mass units in physics, MeV to C square. So divided by C square, we get about 938 mega electron volts. You know that a helium nucleus has a mass which is about 4 times that much, but not exactly 4 times that much. If you calculate the difference between 4 protons, just multiply a proton mass by 4 and subtract the mass of helium. Here it's conducted in atomic mass units, but you can also do it directly in mega electron volts. You find a slight difference of 28.3 mega electron volts between the mass of 4 hydrogens to the mass of 1 helium. So it's almost 4 to 1, but there's some excess energy. And if you divide that excess energy of 28.3 mega electron volts by 4 nucleons involved in the process, you get precisely this binding energy jump on the right from H1, a proton appearing in the left bottom corner, to helium-4 here at just above 7. So you can see it's about 7.04, right? Or 7. Between that and 7.1, it will be exactly the energy gap divided by the number of nucleons. So the binding energy per nucleon in the helium nucleus. It means that something in the helium nucleus is binding the nucleons tighter together, which means they have a lower potential energy or a more negative potential energy, which you can think of as a stronger binding energy. And it's that small gain in energy, which you get from taking 4 unbound protons and binding them together in a helium nucleus, that excess potential energy is released outside as energy output of the process. And this is about, as you can see, 7 mega electron volts per for this overall reaction. So again, about 1 million times stronger or more energetic than typical chemical reactions, which would be the same without the mega, just electron volt. And another type of calculation you can think of, releasing 7 mega electron volts per nucleon, when a nucleon's rest mass is basically around 930 or 940 mega electron volts, gives you an efficiency, netzilut in Hebrew, how much of the mass can you actually use for producing energy, which is almost 1%. It's 0.75%. So compared to chemical reactions, which are 1 million times weaker than this, this is a huge gain in efficiency and a huge gain in energy production. Okay, and these are all calculations that, again, Eddington could follow and could do without knowing that what's actually happening is that 2 of these protons must be converted to neutrons in the process, without knowing anything about the weak nuclear interaction which is required to produce these, to transform these protons into neutrons, without knowing the strong nuclear force, which is what actually holds the nucleus together and gives us this excess potential energy. You don't need to know any nuclear physics to do this calculation. Just know the basic result of Einstein from about 20 years earlier, E equals mc squared. Measure as exactly as you can the mass of a hydrogen compared to the mass of helium, multiply by 4, subtract, and you get this binding energy per nucleon, and you know at least the potential of how much energy you can get out of this system. And because, again, the sun is 90% hydrogen and about 9% helium in fraction of atoms, and this process would produce large amounts of energy in the process of converts hydrogen to helium, this is what we now think and basically know to be the governing process, or overall the governing process, at least the governing budget of energy in the sun. We'll talk about how this process can't happen directly, but at least budgetary-wise, what goes in on one side, what comes out of the other side, this is basically the process that powers the sun. and all the stars on the main sequence, and basically all of our life. Okay, any questions so far? Okay, I'll just add again. We're going up here to the right in atomic number, so in number of nucleons, while climbing up, mostly up in the binding energy. And these are fusion processes. You can see it in a zoom in here on the right side, basically from hydrogen 2 all the way to silicon. This is increasing in number of nucleons and climbing up in binding energy. You can see, and this plot does require some more delicate measurements, that some of these atoms are more stable than others. Some of them will be lower or up. So we won't go through every single nucleus in the process. But we do know that from the same energetic considerations, this process has to stop around this iron peak. There's some point where we can't expect to produce any more energy by fusion. And so we can't expect to produce any higher elements by the same slow process of stably fusing elements into heavier ones.
Perfect.
Yes.
Is the peak the part where the star dies?
Is what?
Is the peak the part where the star dies, where the fuel runs out after the fusion processes?
Yeah, the star will die or will evolve to the next stage in its lifetime when it stops being able to burn hydrogen.
Thanks.
Okay.
Also, may I
yes.
ask a question?
Yes.
It's not that I mean, if we have a star and it has some hydrogen, not hydrogen, iron atoms in it.
Mm-hmm.
It can still produce higher elements. It's just that it will be energy inefficient.
It's energy inefficient, which means you can't do it as a sustained process.
So they will go back, but the net amount they will.
Yeah, you can't produce any substantial quantity of heavier elements because it costs you energy, and of course, if it costs you energy, it removes heat from the star. If it removes heat, it removes pressure, and then gravity pushes you down. We'll actually get, when we do stellar evolution, to what happens at the end of the process where you're stuck with iron and can't burn any heavier elements. And that's where a stellar core will typically collapse under gravity, and you'll have a supernova, basically, or be left with some remnant. It won't continue this stable life of burning elements into heavier ones. You can't do that in a stable fashion if there's no energy gain in it.
Okay, thank you.
Okay. So now when we have this new method of producing energy from a star, fusing 4 hydrogens into a helium, we can do the math, convert this energy back from mega electron volts to 19th century units of joules or joules. And again, we have that each reaction produces 4.5 10 to the minus 12 joule. Might not seem like a lot, but it's, again, 1,000,000 times more than a typical chemical reaction. The luminosity is the same. We have this number from before, 3.8 10 to the 26 watts. If we want to calculate the rate, then we could just divide our luminosity, which is energy per unit time, by the energy per reaction, and we get the number or the rate of reactions in the sun. We have basically 8.5 10 to the 37 helium nuclei produced in the sun every second. And this is inferred by seeing how much luminosity the sun puts out and how much energy each reaction produces. Divide those and you get this huge number of helium productions per second in the sun. If you want to see how long this can be sustained for, then the solar mass again is about 2 10 to the 30 kilograms. If you calculate the number of hydrogen atoms in the sun, then you take basically not all of the sun is hydrogen, so you take the hydrogen mass fraction, 0.71 of the mass of the sun. It's 0.71 because while 90% of the atoms of hydrogen of the sun are hydrogen, it's not 90% of the mass of the sun, because helium atoms are heavier by about a factor of 4, so you have to do the weighted average. And if you do the weighted average, I think who also gave that as a tutorial problem or homework exercise, you get to approximately 71% of the mass of the sun is in hydrogen. And if you divide it by the mass of a single proton or single hydrogen nucleus, they're basically the same, then you get that the mass of a nucleus is very small. It's about 1.6 10 to the minus 27. So you get 10 to the 30 divided by 10 to the minus 27, follow through all the exact numbers. You get about 8.4 10 to the 56 number of atoms in the sun. So that's your total fuel tank. You have 8.4 10 to the 56 hydrogen atoms. How fast can you burn them for? Well, if you produce 8.5 10 to the 37 helium atoms per second, and you recall that every one of these helium atoms comes from 4 hydrogen atoms, then if you take your total number of hydrogen atoms n and divide it by 4 times the rate, that is the rate of consumption of hydrogen atoms, which is 4 times the rate of production of helium atoms, because 4 go into 1, that's basic math. Then you get that this number comes down to, ignoring all the constants, 10 to the 56 times 10 to the 37 brings you up to about 2.5 10 to the 18 seconds, which is about 79 billion years. And now we're in the correct ballpark. Okay, now we finally have an upper bound for the process fueling the sun, which is above the duration of time, which we see as a lower bound from observations on the Earth from geology and biology. And there's still a few orders of magnitude here, maybe 1 or 2, but now our estimates are consistent. The upper bound is finally above the lower bound. So this is a process which can actually work. I see a question in the chat. If the luminosity is observed by the Earth. Okay, so I remind you that what we measure on the Earth is called the solar constant, which is a measurement of flux. That's energy per time per unit area. And it's about 1,300 watts per meter squared. Assuming that the sun is spherically symmetric or emits spherically symmetric, and to a good approximation, you can treat it as spherically symmetric. The granularity that we see is, we don't see very large differences, at least for an order of magnitude calculation, it's fine. Then you can get the total luminosity of the sun if you multiply that 1,300 watts per meter squared by 4 pi r squared, with r being 1 astronomical unit. 1 astronomical unit is 150 million kilometers, so that's 150 billion meters, or about 10 to the 11 meters. Squared, that will be 10 to the 22 meters. 4 pi gives you another factor of 10, so that's 10 to the 23 meters squared. And now if you multiply that by 1,300, then 1.3 10 to the 3 watts per meter squared times what we had, about 10 to the 23 meters squared, you get to this number of about 4 times 10 to the 26 watts. So the total power of the sun is just a surface integral 4 pi r squared over what we measure from the Earth. Okay, today we have satellites orbiting the sun. We can analyze the output of the sun by frequency and see different bands and do all sorts of different analyses. But at least for understanding the main, the order of magnitude of these numbers, that's good enough, and you can do that a long time ago already. Just calculate how much power you get, multiply by the square of the distance of the Earth from the sun. Okay, I will say that this 7 or 80 billion light years 80 billion years, is slightly longer than we actually think the amount of time the sun has to live. And that's because the sun doesn't burn hydrogen everywhere. Conditions for burning hydrogen are very, very difficult. How difficult? Well, we've never been able to stably burn hydrogen into helium on the Earth. While fission processes, breaking nuclei apart, is something that's done every second of our lives in nuclear power reactors. Some countries in the world, like France, produce most of their energy from nuclear fission in a stable, sustained matter. There has never been on the Earth a fusion plant which can stably produce energy by fusion, by fusing two light particles into a heavier one. The conditions required for that are a very, very high temperature, which causes a very, very high pressure and high density, and we cannot produce those conditions or reproduce those conditions on the Earth in a stable manner. The temperature and pressure will just rip apart any device or any plant where you try to do it. Which is why the one place we have been able to do it is in what's called hydrogen bombs. In a hydrogen bomb, you don't care about a slow, gradual process. You want to release it all at once, and you don't mind that the energy released and temperature will rip your device apart because it's a bomb. That's what it's supposed to do. And so we have been able to produce, in some way, a fusion process, not exactly hydrogen, we'll talk about that maybe another time, but fusing a type of hydrogen, heavy hydrogen deuterium into helium. And again, to get to the necessary conditions, the right temperature, what you typically do today is you detonate an atom bomb, a uranium bomb, around a hydrogen core so that the heat from the atom bomb is high enough to ignite the hydrogen. It's that difficult to get hydrogen to actually fuse into helium. It's very difficult to do. So the sun doesn't burn hydrogen everywhere. Conditions are very, very delicate. It can basically only be done in the core. And because the sun, as we'll talk later in this class, and might have actually shown it in the beginning, if we go back to our diagram, recall that this convection only happens near the surface. That is, moving matter around doesn't happen in the core of the sun. That means that there's very, very poor mixing of matter in the center of the sun. So basically, the hydrogen that we see from the outside in the atmosphere of the sun will likely never reach the core and will never get burned. So the amount of actual nuclear fuel available for fusion in the lifetime of the sun is about 10% or something like that of the actual content of the sun, which is why we expect a typical lifetime of a star like our sun to be around 10 billion years and not 80 billion years. And that really puts us in the right ballpark. Today, we think that the sun is about 4.6 billion years old, and so is the Earth. We have an estimate of that from actual rocks and radioactive decay and dating of rocks from both the Earth and the Moon. So now again, geology, aided by physics, tells us these approximate lifetimes of our planet and other objects in the solar system. And so we're basically in the middle of the main sequence lifetime of our sun. And now we understand how that happens. Okay. Not all stars are expected to live for the same duration. And the reason for that is because, again, if our calculation for a life expectancy of a star comes from the amount of fuel the star has divided by the luminosity, that is the rate at which the fuel is consumed, then we can see that for different stars, both of these numbers change. On the right here, we have a plot. Again, this is an observational plot. It doesn't show lifetime. It shows what we can measure directly, which is the mass of a star. We can usually measure masses of stars in different methods from spectra, from pairs, binaries, and other methods. On the left here, we have the luminosity, which again, we measure by magnitude, flux, temperature, and all those things that we covered in last week's class. And we see that there's, along the main sequence, kind of this statistical relation, which shows us that the heavier the star is, the brighter it burns, the brighter it lights, it produces more energy. And what's more interesting is that this plot is on a log-log scale, so factors of 10 on the bottom, factors of 10 on top. The slope is not 1-to-1. It's not that a star that's 10 times brighter, that's 10 times heavier, will burn 10 times brighter. It's actually a much stronger power. If you try to fit the slope of this statistical line, empirical line, it comes out to some number between 3 and 4, and we can take as an average fit something like 3.5. And you can try to calculate where that number comes from the nuclear physics and from the density and other profiles. That requires a more intimate knowledge of the inner structure of the star. But even if you just take this kind of order of magnitude estimate, empirical observational estimate of 3.5, you see that stars that are 10 times more massive will burn maybe 4,000 or 5,000 times more fast, brighter. That means if you calculate this lifetime by just dividing the mass by the luminosity and compare it to the mass and luminosity of the sun, then when it's around the mass of the sun, you can take the luminosity as the same, basically, and you get just this simple scaling. But if you put in that the luminosity actually depends itself on the mass, that is, if you put that L goes like m to the alpha with alpha 3/2, then what you do when you do this calculation is that, again, luminosity is the velocity or the rate of energy consumption. So that's energy, dE dt, change of energy in time. Your available energy is mc squared. That's basically Einstein's relativity, times this number eta, which is efficiency. We said for the sun, it's for hydrogen burning, it's about 0.75%. 0.75%. Wait. 0.75, not percent. So, wait a minute. Order of magnitude, fine. 0.75%. So that's this eta times c squared. dE becomes dm because c doesn't change. Moving this around by saying that this luminosity is proportional to m to the alpha, you get a simple differential equation, which gives you the lifetime proportional to basically one integral of this m to the minus alpha. So you get m to the 1 minus alpha. And this alpha, again, is a rather large number, 3.5, which means that a lifetime of a star is basically governed by how much mass you have, the efficiency, which is approximately the same for everyone on the main sequence, because it's the same hydrogen to helium fusion. So you can scale it by the lifetime of the sun, if you take all the units out, about 10 gigayears times the mass of the sun in solar mass units to the power of minus 2.5. Okay, crucially, the mass here appears in the denominator, which means heavier stars are much brighter, factor of 3.5 in the exponent brighter, which means they're a factor of 2.5 in the exponent shorter lived. The brightest stars will burn much faster than the amount of energy that they have in mass, and they'll die quicker. They'll run out much faster. So again, this means that M-type stars, those are lower mass, lower luminosity than the sun, will live much longer, 100 billion years, even more. They might never actually run out of fuel. But the more massive stars, higher on the left of the main sequence, left and up, can live for maybe a few billion years, hundreds of millions of years, maybe just tens of millions of years. the brighter stars run out a lot faster. And so even though they're much more common, they're much brighter, you'll see much less of them. Okay, they live for a very short period of time. Any questions so far? Okay. So now we are faced with the opposite question, which is, if we can produce so much energy from hydrogen fusion, and we have so much hydrogen in the sun, why is the rate so ridiculously slow, right? We burn about we produce about 8.5 10 to the 37 helium nuclei per second. That means we burn about 34 10 to the 37 or 10 to the 38 hydrogen atoms per second, but the number of available hydrogen atoms in the sun is 8.5 10 to the 56. So there's a discrepancy here of about 10 to the minus 19, which means that every second, only a millionth of a millionth of a millionth of a tenth of the atoms in the sun actually undergo fusion. A ridiculously small number for a process which is exothermic, it produces energy. It also means that if you invert this number, 10 to the minus 19 per second, then you'll get 10 to the 19 seconds, which is basically the order of magnitude of time you'd expect a hydrogen atom in the sun to survive before participating in fusion. And that gives us about this number of 10 or 100 gigayears, depending if you count all the atoms or not in the core or outside. But again, we see that this timeline, this time expectancy of about 10 gigayears, which is just the inverse of 10 to the minus 19 reactions per second, is determined by how unlikely it is for hydrogen atoms to actually go through fusion in the sun. And so we have to ask, why is this process so rare? And the answer is that we now have to look deeper into this process of nuclear hydrogen fusion. And remember that what happens is that the energy gain comes from the strong nuclear force. That is, when you get nucleons very, very close to each other, close enough to bind with a strong force, then you're in the potential well and you get energy coming out. But when they're far away, the strong force is almost not effective. We don't feel it in our everyday life. What we notice in our everyday life is the electrostatic force. And the electrostatic force repels similar charges, as you all learn in high school, right? Similar charges repel, opposites attract, similar charges repel. A proton and a proton are both positive. So if you try to bring them together, they'll push each other apart. If you try to bring 4 of them together at once, that's first of all statistically not very likely, because they'll repel each other, and you need 4 different particles to be in the same vicinity at the same time is very, very unlikely to happen. But also because each of them will repel each of the others, and they'll repel each other very strongly. So it actually turns out, if you do the calculation, that it's completely impossible to fuse 4 hydrogen or protons, 4 hydrogen nuclei, 4 protons together at once to form a helium atom, a helium nucleus. The process is ridiculously unlikely, and it doesn't happen in the sun. The repulsion, the electric repulsion between protons is much too strong. 4 to 1 cannot work. So you have to do this process in stages. And the first and most important process of burning hydrogen into helium, fusing hydrogen to helium, is called a PP chain, or proton-proton. PP is proton-proton processes. And there are different types of these chains, but what they basically say is that you can only do reactions 2 at a time. The first chain Okay, and we'll talk about what these chains are exactly. In general, what they mean is that you merge two protons together and to form a couple. That pair will not be helium because there are no nucleons, no neutrinos yet, no neutrons yet. It will be heavy hydrogen or deuterium, changing one of the hydrogen or one of the protons into a neutron. Then when you have two deuterium nuclei, then you can merge them together for helium. You always do the process in pairs. I see a question. Do the protons meet at the same random point? Well, for the two protons to undergo fusion, to merge, whether it be two protons producing a deuterium atom or two deuterium nuclei merging together to form helium, or one deuterium meeting another proton or another neutron to form tritium, or any of these processes, you would need the two components, say for simplicity, two protons. They can never occupy the exact same point, but you need them to come close enough for the strong force to become stronger than the electric repulsion force. And that's exactly what we see in this diagram here in the center. When the two protons, for example, or any two nuclei with atomic numbers Z1 and Z2, that's the charges, basically, charge Z1 and charge Z2, both of them are positive because we're talking about nuclei. Far away, what they feel is the Coulomb barrier, the Coulomb force, which is repulsion. So Z1, Z2 times E squared, or if you want, Z1E is the charge of one nucleus, Z2E is the charge of the second nucleus. Multiply them together, you get Z1, Z2, E squared divided by R. That's the potential. And because all of these numbers are positive for nuclei, then this barrier is positive and repulsive. There is an energy gain relative to infinity, relative to free particles. That's the strong nuclear gain. That's very, very close in. And that, of course, is what we saw in the diagram. The binding energy of the new nucleus, for example, deuterium, if you merge two protons together, is negative. It's better to have a deuterium atom than to have two protons energetically. The mass is lower, which means energy was released. But this only takes effect very, very close to each other on the range of action of the strong force, which is the range of action of the strong nuclear force, which is basically the size of a nucleus. The size of a nucleus is about 1 femtometer, so, or 1 Fermi. So that's 10 to the minus 15 meters. Okay? Now, we can calculate how big this barrier is. The barrier is, take a number that you know, for example, a hydrogen atom, now an atom with an electron. You know that the innermost orbit or shell is at minus 13.6 electron volts relative to infinity. That's the ionization of the innermost electron around one proton. That number is exactly equal to 1 times E squared, or rather 1 times minus 1 times E squared, divided by the radius of the innermost orbit, which is 1/2 angstrom, right? That's the Bohr radius of a hydrogen atom. And the charges are the same, 1 electron times 1 proton. It's just a sign flip, but the number is the same, minus 13.6 electron volts. But that's at a radius of 1/2 angstrom, so 1/2 10 to the minus 10 meters. If you want to go to 10 to the minus 15 meters, which is the size of the nucleus, which is where the strong force will finally take effect, then this R has to go down by a factor of 10 to the 5. It's 100,000 times closer. So the energy will be 100,000 times bigger. So from 13.6 electron volts, say 10 electron volts, multiply by 100,000, you'll get to about 1 million electron volts. And that's exactly this number here, this order of magnitude that we find here on the right. The Coulombic energy barrier for fusing two protons together is about 1 million electron volts. And again, it becomes the radius you need to bring them into, about 1/2 10 to the minus 15 meters. So it's 100,000 times more difficult than the energy required, for example, to ionize a hydrogen atom. Okay, so we talked about this potential barrier being very high, 1 mega electron volt. How do we cross it? Well, the naive way would say the solar core is very hot. As we said, it's about 16 million Kelvin. Maybe statistically, we'll calculate a Boltzmann factor. You know, it's a gas, plasma gas. The protons have a very high temperature, so they have very high energies typically. Some of them are bound to have very, very high energies. Let's see if any of these energies, very energetic protons, can cross this barrier. And let's calculate how many of them and what would be the rate of protons crossing the energetic barrier. Okay, so the temperature of 16 million Kelvin converted to electron volts is about 1,300 electron volts, because 1 Kelvin is about 11,000 electron volts if you multiply by Boltzmann's constant. But this is still very weak, right? 1,300 electron volts is about 1/1000th of a mega electron volt. So our typical proton is still 1,000 times less energetic than it would need to be to cross the potential barrier. Okay, that's fine. That's just the average proton. But maybe the tail reaches high enough into high energetic protons. Okay, well, we have a calculation of tails, and these are very high temperatures, so we can ignore the Fermi or Bose-Einstein statistics. We can just take a Boltzmann approximation, calculate the Boltzmann constant, which is e to the minus exponent of minus e over kT, right? This is the Boltzmann constant you know from thermodynamics. How unlikely is a process to happen, or how unlikely are we to have a proton of such high energy? And if E is about 1,300, and sorry, if E that we need, the energy we need to cross is 1 mega electron volt, and K Boltzmann T, the temperature that we have, is about 1,300 electron volts, then we have about a factor of 1,000 in the exponent, or rather minus 1,000, and e to the minus 1,000 is 10 to the minus 400 approximately. Okay, so if we look at the core of the sun, out of every 10 to the 400 protons, 1 will be energetic enough to actually cross the barrier and reach another proton. This is a very small number, or rather 10 to the 400 is a very large number, because again, the sun is big, but it's not that big. The sun only has 10 to the 57 hydrogen atoms, and there's a factor of about 10 to the 350 between these. Okay, so you basically need a star 10 to the 350 times the mass of our sun for this process to work. Quick order of magnitude, there are 10 to the 10 stars like our sun in our galaxy, and about 10 to the 10 galaxies. So the entire mass of the universe is about 10 to the 20 something solar masses. We need 10 to the 350. This means there is not a single proton in the entire universe, in any star in the universe, which is actually energetic enough to climb this potential barrier and undergo fusion classically. Question: is it dependent on the volume? It is slightly dependent on the volume. Some processes will be more dependent on volume than this one. The reason this one is almost not dependent on volume is because of the sheer proximity which we need to come here, right? So the density in the center of the sun, as we'll see later on, is about 150 grams per centimeter cubed, which is large. Water is about 1 gram per centimeter cubed. So we're talking about densities about 100 times more than that. Most solids on Earth can have a density, sand and rock will have densities of about 2, 3, 4, 5. Metals, gold might have up to 10 or 20, something like that. We're talking about something that's very, very dense indeed in the center of the sun, but still, we're orders of magnitude away. If we talk about densities on Earth, which are basically chemical densities, even for solids, two nuclei do not come closer than the distance between the innermost electron to its own proton, which is, like we said, is the order of an angstrom. And here we need to come 100,000 times closer. 100,000 times closer in distance means the density would have to be 100,000 times cubed to be dense enough for atoms to come that close. So we need to come 10 to the 15 times the density that we find on Earth to actually make this process happen from density. Basically, we'd have to go to nuclear densities, and that doesn't happen in the sun. Okay, so in this case, when two protons see each other and when we ask if two protons can actually go fuse with each other, in the small volume that's involved, basically they can think of themselves as the only two particles in the universe. And up to about, maybe 10,000 times further away, they still don't see any other particle. So here volume is not significant. Density and volume are not significant that much. Okay. So this process classically cannot happen. Yes.
I also have a question. I didn't understand how was possible that two protons can become a deuterium, which is a proton and a neutron? Like how the charge changed?
It happens under a weak interaction. That's the weak nuclear force. It's required to change a proton to a neutron. That's maybe in the next slide, maybe one after that. It will have to be a weak interaction. But we're not even there yet, right? Now we're talking about even if it did happen, you'd need that to happen when they're close enough together, and they're still not even able to get close enough together, classically. But quantum mechanically, they are able. It is possible. Quantum mechanically, we have another effect, which is called quantum tunneling. Let me just fix this here. Okay. Quantum tunneling. Quantum tunneling tells us that even processes which are impossible classically can sometimes happen quantum mechanically, because the wave function of a particle is not identically zero in the region which is classically forbidden. That is, if you have a barrier, a potential barrier that's very, even if it's very, very high, the quantum wave function can still penetrate from outside inwards with a lower energy. See the energy here on the outside represented as being lower than the peak of the potential. It's lower than the barrier. It doesn't go over the barrier. It tunnels through the barrier. And if the barrier is narrow enough, then this region that's classically forbidden and quantum mechanically causes an exponential decay in the wave function and in the probability for finding a particle there, if it's short enough, then the decay is not very significant. And then you can find the particle under the barrier and passed through the barrier, into the left side here, and even to the region where you can get an energetic gain. Okay, you can think of this as if you want to drive, for example, from Tel Aviv to the northern border, to Akko, to Nahariya, and you want to go through the Carmel Mountain in the middle, if you don't have enough gas, you'll never have enough velocity or kinetic energy to climb the Carmel Mountain and then go down the other side. You'll be stuck at the potential barrier. But today, the Carmel Mountain has a tunnel going through it, which is basically level at the height of water of the sea. And so you can go through one side, through a tunnel through the mountain, and out the other side. And theoretically, if the tunnel is short enough, then you'll pay less for going quicker on the inside than you would have needed to climb all the way up and back down. So this is quantum tunneling, and that's basically what allows for this process to happen. Because the probability of quantum tunneling, that is, if you have a high energy proton of an energy E, then the probability of crossing a barrier basically goes like 1 over the square root of E, which is a factor that changes very slowly, times this exponent of minus eta. I'm neglecting constants here. You can see that eta goes like the potential barrier, right? Z1, Z2 times E squared. This is the Coulombic potential barrier, divided by the square root of the energy. And this is when you consider that the radius was in the denominator of the potential, but it all working against you, but it also works for you because you basically need to cross the integral of this barrier, or rather the area, the height times the distance. Classically, you need to climb over the barrier. It doesn't matter classically how wide it is, it only matters how tall it is. So the shorter it is and the higher it is works against you. But quantum mechanically, it doesn't matter separately how tall and how wide it is, it's only the product. And so if R is very small, which makes the potential barrier very high, still the product of the width times the height is basically a constant. And so you don't care anymore that the potential barrier is very, very tall, is very high, because it's as short, as narrow as it is high. That means that the energy comes in here as a square root in the denominator. So when the energy is very big, eta becomes very small, and then minus eta becomes again very big. And so the probability of a high energy particle crossing or tunneling through the barrier becomes exponentially large. And that's what we see here on the right plot. As particle energy grows, the probability of that particle to go through the barrier and fuse is exponentially growing. There is still the Boltzmann factor, which tells us that at a given temperature, the chance of getting a high energy particle is exponentially decreasing. But we no longer have we no longer have to get particles of the order of 1,000 times the energy that they would normally have, or 1,000 times the temperature. This Boltzmann factor will no longer be e to the minus 1,000, because the energy E that we now need is much lower. Because again, we no longer need to climb the potential. Now we just need E to be high enough to tunnel through the potential, which means the overall probability of a proton at temperature T to tunnel and to fuse is a product of this Boltzmann factor, which is exponentially decaying, times this tunneling factor, which is exponentially growing. And if you multiply a growing exponential by a decaying exponential, you get a very, very sharp peak called Gamov peak, after the Russian scientist who realized this idea in the, I think, late 40s. And this is how nuclear fusion can actually happen in the sun. It's inherently a quantum mechanical process. You need a proton to tunnel through the barrier of another proton. So you need temperature still to be very high in order to have enough high energy protons. But once the protons have modestly high energy, not ridiculously high energy, the tunneling probability already grows, and they can tunnel through and go through fusion. Question, how was this proven? So you can answer that question in multiple ways. One is calculate the rate and see that this basically matches the rate of reactions you see from the sun. That's an indirect calculation. Another thing you can do is you can measure quantum tunneling in a lab in a simpler system. For example, you can construct potential barriers for electrons and see that the electron can tunnel through barriers, and this is classical quantum mechanics. Again, an analogous system, not direct evidence. The direct evidence, which we have had for the last few decades, is seeing the result of this process, which, as I said earlier, was neutrinos coming from the sun. Neutrinos come from conversion of protons to neutrons through the weak nuclear interaction, and that's basically what happens for this process as part of this process. So now we have direct evidence, and now we have a measurement of what those neutrinos are and different types of neutrinos, and now this is well established. But yes, for Gamov's time, this was, of course, a huge theoretical proposition, using quantum mechanical tunneling to answer this 10 to the 400 factor discrepancy in rates versus potential barriers. Okay, this makes the process possible. It still doesn't make it too likely, right? This is still difficult. You have an exponential decay. We still need energies to be very high. It's no longer completely impossible, but it's still possible, but slow. And not only possible, but also very narrow, as we said. The peak in energies is very, very narrow, which means that there's a very specific temperature at which this process can happen. And because there's a dependence in the exponent on Z1 and Z2, and on the mass, it means that particles of different atomic charge, that is different elements, will be fusing and tunneling at very, very different energies and very, very different temperatures. What that means basically is that if you have hydrogen fusion, you will not have helium fusion. If you have helium fusion, you will not have hydrogen or carbon fusion. It means that if temperatures are high enough, you will get basically layers of different types of elements burning, and these layers will be rather narrow and rather constrained. There's only a specific temperature at which the Boltzmann factor is not yet completely gone, and the tunneling factor is reasonable. So these Gamow peaks are very, very sharp, which is also good because if you see hydrogen burning, you basically know what the temperature is because the rate is very sensitive to the temperature. Okay, let's take a 10-minute break until 2:05, and then start going deeper into the stages of the PP chain burning hydrogen into helium. There, we're back on. And so we talked about what has to be the overall process in the sun. It has to be conversion of 4 hydrogens into a helium. That's what the matter that we have in the sun. That's the process that can produce the proper amount of energy. It's a process that can sustain the sun for as long as we see. We talked about how difficult it is to actually trigger that process. We said that it's impossible entirely if you try to make 4 hydrogens collide at once to produce a hydrogen atom, a helium nucleus, but that it is at least possible, if still difficult, if you do it in pairs, pair by pair, using quantum tunneling. And so now let's see what is this process or this chain of pair reactions that goes from 4 hydrogens into a single helium atom. And the first of these chains, the most important in our sun, called here number 1, is the PP chain number 1, which looks as we see here on the right. Notice each interaction has 2 incoming components. On the left, for example, we have 2 hydrogen nuclei, so 2 protons. It's very hard for them to meet, as we said, but if they do come close enough together, then they can undergo the following double process. The first is that one of the hydrogens will change into a neutron, emitting a neutrino, and an anti-electron or a positron. That is, the charge of the hydrogen nucleus, the charge of the proton is carried away by a positron, and the change in basically an up quark inside the proton to a down quark is mediated by the weak nuclear force, which causes a neutrino to emerge from the system. Okay? Together, if this happens close enough to another proton, then they'll basically merge together, and the process doesn't typically happen on its own. Neutrons on their own are unstable. They don't survive on their own. They can only survive with other nucleons attached to them, protons, etc. So if this happens at the same time with another hydrogen nucleus with another proton, then we get finally a pair, 1 proton and 1 neutron, and this is called deuterium. It's an isotope of hydrogen, so H2, 1 proton, so it's still hydrogen, but a mass number of 2 because it's a hydrogen, it's a proton and a neutron. And this is written here on the top left. 1 proton plus 1 proton, creating a nucleus, which is now deuterium, atomic number 1, mass number 2, heavy hydrogen, plus, as we said, the weak interaction remnants, which are a positron and an electron neutrino. This process itself is exothermic. It produces energy, a small amount. It produces 0.42 mega electron volts. But importantly, because the weak interaction is involved, this is actually a very, very slow process. The weak interaction is much weaker than the strong interaction. So whenever something relies on the weak interaction, it takes a very, very long time until it can actually happen. In this case, under typical conditions, the rate for this process is about 8 billion years. Okay, and this is what dictates in the end, the rate of nuclear fusion in our sun. It means that a random pair of protons will go through this, will take 8 billion years to undergo this interaction in the sun, because it's a very, very slow process, which requires a weak interaction, changing a quark, changing a proton to a neutron. The rest of the process is actually quite fast in comparison, because as you can see from the diagram on the right or from the list on the left, the next stages do not involve neutrinos, which means they do not involve the weak interaction, only electric interactions and strong interactions. So the first one is that this deuterium can now fuse with another hydrogen nucleus, so another proton, and produce now an isotope of helium, helium-3. So 2 protons means that it's a helium atom that chemically will behave like helium. But there's another neutron, so it's not the most common isotope of helium, helium-4. It's slightly lighter, helium-3. This is the third line here on the left, 1 deuterium plus 1 standard hydrogen, producing a helium-3 isotope, and gamma rays, that is photons. With an energy output now much greater of about 5.5 mega electron volts per interaction. Now this energy, of course, is distributed between the helium remnant and the photon remnant. So you can see how much of the energy will go in either direction, but basically the output is 5.5 mega electron volts. The 0.42 mega electron volts, by the way, produced in the first line in the proton-proton, the PP fusion for producing deuterium, will also be distributed among the deuterium nucleus, the positron, and the neutrino. And it gives us kind of an estimate of the the highest amount of energy that these neutrinos can have. And so when we observe this process from the Earth, we actually don't observe any of these photons. As we'll talk next week, photons produced in the core don't actually make it outside for millions of years. We'll only see them as thermal radiation much, much later. But these neutrinos have basically no interactions with the other matter in the sun, because again, neutrinos are involved in weak interactions, which are very weak, so they hardly ever happen. And so these neutrinos we can see directly. And by measuring the energy spectrum or the energy distribution of the different neutrinos that reach the Earth, we can infer what nuclear process involving them or creating them is happening in the sun. So this comes directly from calculating the surplus energy and the different cross sections of nuclear processes involving neutrinos produced in the core of the sun. Okay. Also, the positron doesn't survive for very long. Effectively, instantaneously, it is gone, because as we said, the state of matter in the sun is plasma, especially the core is completely ionized plasma, which means there are loads of electrons floating freely around, and in a fraction of a fraction of a fraction of a second, this positron will meet an electron. They attract each other because they are of opposite charges, and when they meet each other, the electron and the anti-electron, which is its antimatter particle, the positron, annihilate each other, and all the energy gets converted into photons. So the pair annihilation of the electron-positron pair producing a pair of photons gives off about 1 mega electron volt in the system of the center of mass. So each of these photons will have about half of this energy in the center of mass of the system. So what we're left with, again, neutrinos escape outside. We can measure them at the Earth. Positrons get annihilated and produce even more heat energy in the form of photons, which later transform into heat energy. So we're left with another photon coming off. In the end, these three lines, or this three-stage process, gives us helium-3. At the same time, we have more helium-3 forming from other pairs of protons floating around in the core of the sun. And when these two helium-3 nuclei meet, then they can fuse. Again, it's a difficult process because the charge now is 2, so there's even a stronger potential barrier. But on the other hand, no neutrinos are involved, so we don't need to wait for the weak interaction. So the time scale for this process, this final step, is about 240,000 years. So not very short, but much quicker than the weak interaction mediated proton-proton conversion into deuterium. So these two heliums meet, helium-3 meet. In total, we have 6 nucleons. 2 of them are surplus. So 2 protons get ejected out of the process back into the core to undergo other stages. And 1 helium-4 nucleus is produced. 2 protons, 2 neutrons. This final step gives us another excess energy of about 12.86 mega electron volts. We can see that directly, by the way, in our isotope plot. The jump from hydrogen-1, a proton, to deuterium is actually not very large. It's 1 mega electron volt per nucleon. But the jump from helium-2 to helium-3 we see is another about 1 mega electron volt per nucleon. But the main jump from helium-3 to helium-4 is 4 mega electron volts per nucleon. And because there are now 4 nucleons involved, we get this large number, about almost 13 mega electron volts for this final stage. Summing it all together, we get twice pp to deuterium, twice electron-positron annihilation, twice deuterium absorbing a proton to produce a helium-3, and 1 time a pair of helium-3 is producing helium-4. the total energy gain in this process is 26.7 mega electron volts per reaction. This is not exactly the 28.3 we mentioned in the beginning, but you can kind of find the missing energy if you consider that we didn't treat the rest masses of the positron and electron involved. So this process actually also consumed, if you want to look at the net process, it consumed 2 electrons. Okay, there's an error in this slide. There's a 4 missing here in front of the hydrogen. Of course, 4 hydrogen atoms in total are used, as well as 2 electrons. Their total energy is then redistributed to 1 helium-4 nucleus or ion, plus 2 electron neutrinos and a lot of photons carrying energy around. So total of net energy of 26.7 mega electron volts, if you consider it this way. The rate, again, because it only happens in gamma-Voss peak, is very sensitive to temperature. It goes like T to the 4. It starts off, it ignites at about the temperature of 10,000 Kelvin, which is about the temperature we expect from the core of a star of approximately 8% of a solar mass, which is about 80 times the mass of Jupiter. And that's the demarcation line separating between gas giant planets and very, very small or light stars. The first stars, the red dwarf stars, the M stars, the very light M stars, will start at about 1/10 of a solar mass, because that's where they can start fusing hydrogen. At lower masses, the pressure will be lower, the temperature will be lower, they'll never get to hydrogen ignition. And then they'll remain as either brown dwarfs, which we'll talk about later, or just planets. That's why Jupiter is a planet and not a star. It's not heavy enough to be hot enough to fuse hydrogen, even in this process. Okay, so planets don't produce nuclear energy, and stars do produce nuclear energy stably. Our sun's core is, like we said, about 16,000 Kelvin, 1.57 10 to the 7 Kelvin, which means that this is actually the main process in the sun. It works even faster than at the limit of 10 to the 7. It's not the only process in the center of the sun, but it's the main one. The PP chain 1, converting 2 protons into helium-4 in this manner. Questions about the PP chain number 1?
Yes. I wanted to ask the first the first step.
Yes.
Are the helium ones that are created hydrogen that are created very energetic to have a lot of interactions in the core, which gives it the excess energy?
You mean hydrogen 1?
Yeah, hydrogen 1.
Just protons?
Yeah.
Do they exist in the core?
No. Are those like the excessive energy we get from the last interaction? Because we get excess energy that's being distributed in the core, right?
So in the core, you have a lot of protons, basically. If 2 of them happen to meet and go through this process, another 2 go through the other process, then in the end, the net process is that these 4 hydrogens will produce helium and 2 electron neutrinos and a lot of photons going around. Now, the energy is distributed among all of the products of the process. So the nuclei, the positrons, the gamma rays, the neutrinos. But of all of this energy, okay, the neutrinos just take it away and don't do any more interactions. But the gamma photons and the nuclei themselves, they don't really get out of the core, because they immediately bounce against another ion. Or if it's a photon, the photon will scatter off an electron, an atom. It'll go through many interactions. A very, very large number of interactions, which means basically all of this energy produced, except for the energy of the neutrinos, almost all of the energy produced will eventually turn into kinetic energy of different particles in the star. So it will heat the core. Okay.
Okay, so that's the energy.
So the star is in equilibrium. It radiates away a very large luminosity. Where does that energy come from? It comes from energy produced in the core as kinetic energy of particles and radiation energy of photons. And on their way out, they bounce each other millions of times and transfer the energy basically into kinetic energy and keep heating the star.
So that's where the final step gets its most of the energy from the two hydrogens just giving kinetic energy to other particles?
Yes, the two hydrogens are now going to have a very high energy, and the helium as well. And then the kinetic energy will be redistributed. But also the photons, all of this energy, except for the neutrinos which go out uninterrupted, all of the energy produced here is in the form of kinetic energy, either of photons or of nuclei, or electrons and positrons, and it will stay and circle around and bump around and be distributed and heat the core of the star. And from the core, the heat will diffuse outwards in heat transfer methods, which we'll talk about next week. So eventually the heat will reach the surface and will radiate, and that's what we see, the radiation basically from the surface. Is it possible for a chain to add 2 protons, then another one and another one, so 6 instead of 2 and 2? Is that the question?
אפשר לחבר 4, כאילו 1-1 פשוט, במקום 2 ו-2 שנפגשים ביחד.
Okay, so if you want to add, basically what you're saying is if we can take like the left chain here, 2 protons to deuterium, another proton forming helium-3, and then directly absorbing another hydrogen. I can't see a reason that can't happen on a priori, except for the technicalities might make it more difficult. One is that now you're trying to get a single proton to enter a helium-3, so the charge is higher, so your potential barrier is even higher, so the chance of that happening is even weaker. Also, because you're looking to produce helium-4, you'll need a weak interaction. You'll need a proton to change into a neutron to get helium-4, which makes it an even less likely process because weak interactions are very, very rare. So those are 2 reasons that this process might, if not impossible, might be very, very rare in comparison to this main process. You can also look at the possibility of maybe producing, absorbing the next proton as it is and producing lithium-4, so 3 protons and 1 neutron. For that, you'd need to go back to an isotope table like this one and see if it's even possible. And I don't see even a semi-stable lithium-4 atom on the table. So that process is probably even less possible. It might be, the strong force might not be enough to hold that together. Okay, so this was PP chain 1, the most common process in our sun. But it's not the only one. There are other options of PP chains, namely PP2 and PP3. So the PP chain in our sun is about 69% of the nuclear processes. You can see it here. Basically, they all start the same way. Protons forming deuterium, and then a deuterium absorbing another proton to form helium-3. In the PP chain 1, 2 of these helium-3s, as we said, will produce helium-4 and access to 2 protons back into the core. But in 31% of cases in our sun, that's not what happens. In our sun, because there's already helium-4 available, the helium-4 can actually fuse directly with helium-3. And if you count the atomic number and the mass number, you get 4 protons, which is element number 4, beryllium, and you can form beryllium-7 plus some excess gamma radiation. The process will not end there. Beryllium-7 is not stable, so it will absorb one of the electrons floating around. Again, absorbing an electron to the nucleus means that you're changing the charge of the nucleus, and you're changing one of the quarks into a different particle. In this case, you can see that the mass number 7 remains, but the atomic number 4 goes down to 3. So one of the protons transformed into a neutron by absorbing a negative charge and turning from positive to negative. This again requires a weak interaction, and so it produces, again, an electron neutrino. And this happens about 30% of the time in our sun, or 99.7% of the 31% of time where helium-3 meets helium-4 directly. And we can measure this, again, because this process is at different energies than the first stage, which means the neutrinos produced in this process will be different in energy distribution than the energies of neutrinos in the first stage. So if we observe all of the neutrinos coming from the sun, we can do statistics on them in distribution in energy and kind of directly measure these different processes happening in the solar core. Okay, the lithium-7 itself is also not stable. You can see it's not really, doesn't appear on the isotope chart as a stable one. It will absorb another proton and then decompose through fission into 2 helium-4. So again, the overall process is that protons meet and produce helium-4, but in this case, they took kind of a detour, producing beryllium, producing some lithium, and then producing a double amount of helium at the end. So in this case, 8 protons in the end would have created 2 helium nuclei. The last and rarest pp chain in our sun is pp3, which is starts like pp2, but then the beryllium can absorb directly another proton before decaying to lithium. And then you get boron, which is atomic number 5 and mass number 8. This boron itself is unstable, so it will go through a weak interaction, in this case, a reverse beta decay. It will produce a positron or an anti-electron along with a neutrino, and one of the protons will turn into a neutron. So the mass number remains the same, but the atomic number goes down by 1. And again, this beryllium-8 is itself not stable, so it will quickly break apart into 2 helium-4s. So overall, we have 3 different types of pp chains. All of them start with hydrogen, net proton hydrogen 1, and in the end produce a certain amount of helium-4. And of course, photons, gamma rays produced along the process, which are absorbed and heat the stellar core. And in the end, and neutrinos coming along the way, and you can count the amount of different reactions by the types of neutrinos that are produced. Any questions so far? Okay. Another process is not a pp chain, that is starting from net having only hydrogen, finishing with only helium. Another process that can happen in stars, and it happens in our sun, even though slightly less, is a type of cycle called a CNO cycle, or carbon, nitrogen, oxygen cycle. That happens if the core has, to begin with, some carbon, and it's a cycle because the carbon, nitrogen, and oxygen are not produced. If there's no net production in the process, they are recycled. They just act as catalysts. That is, they speed up the process of hydrogen fusion into helium. And how do they do that? A carbon, typical carbon, carbon 12, the common type of carbon, can absorb one proton and turn into an unstable isotope of nitrogen, nitrogen 13. This is just absorbing a proton, so no weak interaction involved. It releases about 2 mega electron volts in a gamma photon. That nitrogen, if we see it on the left, on the right here, this is the carbon. It absorbed a proton, emitted a photon, and turned into an unstable nitrogen 13. Being unstable, the nitrogen will undergo inverse beta decay. That is, one of the protons will turn back into a neutron. So we'll go down in atomic number from nitrogen 13 to carbon 13. So mass number is the same, but proton number decreased by 1. The charge goes away with a positron or an anti-electron. And of course, you have to emit a neutrino in the process because it's a weak interaction mediated process. But it's a spontaneous decay, and it only takes a half-life of about 10 minutes. So it's a very efficient process, more efficient if you can produce it than the PP chain, because if you recall the PP chain, the first weak interaction, turning the one proton into a neutron or 2 protons into deuterium, took 8 billion years because it was not spontaneous. You needed to overcome a very, very difficult potential barrier and wait for a weak interaction for that to happen. In this case, the nitrogen itself is unstable, nitrogen 13, and so it spontaneously decays to carbon through the weak interaction at a very, very fast half-life. So if you can actually have enough carbon in your stellar core, this is a much faster process, much more efficient. Okay, it doesn't end there. The carbon 13 can then absorb another proton, turning into nitrogen 14. Nitrogen 14 is the stable type of nitrogen, so it doesn't go through spontaneous decay. But like carbon, it can also absorb another proton, emit a gamma photon, and turn into an unstable isotope of oxygen, oxygen 15. This oxygen 15 is unstable. It will go through a similar spontaneous inverse beta decay with a half-life of about 2 minutes and turn back into nitrogen 15, which can then finally absorb another proton, breaking it apart into carbon 12 and a helium, and the excess nucleons break off as a helium nucleus. So this is a cycle. You started with a carbon nucleus, you finished with the same carbon nucleus, but you absorbed 4 protons along the way, converted 2 of them to neutrons in inverse beta decay, emitting neutrinos, and finally released these 4 protons, 2 of them now neutrons, packed together as an alpha particle, helium nucleus. And if you sum up the energies along the way, it comes to the exact same number because the net process that you did here was convert 4 protons into 1 helium-4. I see a question. Is the half-life and binding energies a theoretical result or experimental observation? I think early on they were completely observational, experimental. Now there might be some theory involved, but at least for the basic particles, I think there's still experimental results, observational results. You can look at the PDG, the particle data guide of all measured basic interactions, and they would basically have these numbers measured to a very exact, to very good precision. And of course, theorists will try to explain why this happens and calibrate various models of strong and weak interactions to match these observational results. Okay, so we said that this is a much faster process. The half-lives here, the delay times are very, very short, but you need to have C and O present. And because C, N, and O have much higher charges, 6, 7, and 8, as nuclear charges, the potential barriers for absorbing a hydrogen a proton are much heavier, are much higher, 6, 7, and 8 times higher, which means the required energies are much higher, which means the ambient temperature must be much higher. So this only starts off around our sun at 15,000 Kelvin. You first reach a temperature high enough to actually do this process. Our sun is 1.57, 10 to the 7, so slightly above it, which is why this happens in the sun, but is not a dominant process. But very quickly it becomes dominant above 17,000 Kelvin, which is the cores of stars about 1.5 solar masses. This becomes quickly the dominant process, and the rate here depends even stronger on the temperature. So as the temperature increases, the rate grows like t to the 17th, as opposed to t to the 4, which was for the pp chain. So for massive stars and warm stars or hot stars, this becomes a hugely important process, very rapid, and this is the dominant process in those stars. Okay.
In which stars? I couldn't hear you.
What?
In which star is this more dominant? The CNO?
It is dominant at core temperatures above 17 million Kelvin, which means stars above 1.5 solar mass.
Okay.
So G-type stars like our sun, or M-type stars, it would be the PP chain would be dominant, and above 1.5 solar masses, in hotter stars, heavier stars, it will be the CNO cycle. You can kind of start understanding that this higher mass of a star, which means a higher temperature in the core, which means much more effective and fast nuclear energy production, will be the reason that high mass stars have luminosities which are so much higher than our sun, right? And we talked about the 3.5 exponent in relating the luminosity to the mass of the star. Okay, even higher temperature, at even higher temperature, or alternatively, you can think of it as when the hydrogen runs out, obviously nuclear production, nuclear synthesis, nuclear fusion doesn't stop with helium. We have more elements than that. And the most important process after that is the triple alpha process. This is burning helium. So we mentioned before that helium can actually come from beryllium-8. Remember in the pp chain 3, we have beryllium-8 breaking apart into 2 helium-4 nuclei. The reason for that is that beryllium-8 is unstable. 2 helium-4s are actually more beneficial energetically than 1 beryllium-8. That's exemplified here in having a negative energy gain for this process. So the spontaneous direction is from right to left, not from left to right. The beryllium-8 has a half-life of about 10 to the minus 16 seconds. So it's very unstable. But if during those 10 to the minus 16 seconds, there's enough helium-4 and it's energetic enough that the beryllium meets and fuses with another helium, then you can directly produce carbon-12. And it's a fast process. There's no weak interaction involved. You just need to overcome the potential barrier, and you need to do it fast enough before the beryllium breaks apart into helium. So it produces 2 gamma photons, an energy of about 7 mega electron volts, less than the pp chain. It's less efficient in energy than hydrogen to helium production, but it is a way to produce energy if you have enough helium and if it's hot enough after the hydrogen runs out. Because this process is so delicate, it has to happen very fast before the beryllium decomposes, and it has to overcome a potential barrier of Z1 equals 8, Z2 equals 4. So the potential barrier is 32 times higher than the proton-proton potential barrier. The temperature needs to be a lot higher, and this actually only starts at about 100 million Kelvin. So about 8 times hotter than the core of our sun is where this starts. And also because now you really need an almost three-particle interaction. That is, two particles merge, two helium merges to form a beryllium, but the next helium has to come really, really fast before the beryllium decomposes. You can think of it as a three-particle interaction, and that's why it's not just, this one will not just be dependent on temperature, it will also be dependent on the density, basically the density squared. Because if you have one particle, you don't just multiply by the density, which is the chance of another particle coming. You now need two particles to come simultaneously, so you multiply by the density squared. So it's a much more sensitive process. It requires much higher temperature. The temperature dependence is also a lot stronger, T to the 40, and the density is now also important. So this will be almost completely, if not entirely insignificant in our sun at the present. It will become important in our sun later on when the hydrogen runs out, and then the sun will actually move into burning helium in this triple alpha process. This itself is also not the end, of course. The carbon can still absorb helium-4 and turn into oxygen and move further down the cycle with heavier and heavier elements.
Perfect.
Yes.
I have a question about the triple alpha process.
Yes.
If for example, two helium collides and create a beryllium.
Yes.
But because the temperature isn't high enough, then it will not decompose. How do you say it?
Yeah, it will break back.
Fission. It will decay back to probably two heliums.
Yes.
Then I imagine this net process will be equal to a loss of energy, right?
The net process will be zero energy because you started with two heliums and you finished with two heliums.
But in the meantime, for example, when the helium and the helium collided and created the beryllium, they shoot out a gamma ray according to the diagram.
No. Okay. So if you look at the net process, you see that there's a negative number here. So the beryllium is actually less energetically efficient than two heliums. What that means is that two stationary heliums can't actually fuse. They don't have enough energy to produce beryllium in the center of mass frame. So the helium atoms, nuclei themselves, need to be very energetic, not only to overcome the potential barrier, but because they need the excess kinetic energy to turn into the mass of the beryllium. So this photon comes from the excess kinetic energy, or rather, you need to have a lot of excess kinetic energy. Some of it will go into producing the excess mass of the beryllium, about 100th of mega electron volt, and the rest will go into a photon. But then if the beryllium breaks apart, then it can release, again, the excess energy as either kinetic energy or into more photons, and the net process is zero gain. That is,
okay,
you needed to borrow energy, kinetic thermal energy from the environment to produce this process, and if it breaks apart, then you return the excess energy to the system. It's a net zero process. Photons are emitted along the way. Okay, so energy is taken from kinetic energy, turned into photons, but then photons go away and the kinetic energy goes back into the system, and the photons themselves get scattered and absorbed and the kinetic energy goes back into the system. Net, it's a no gain process.
Okay, thank you.
Okay, this is a short summary of these three different processes by temperature. So log of temperature is here on the bottom, and epsilon is basically the rate or the prominence, how much of it happens in different stars. We can see that at low temperatures, PP chain is the first thing that kicks off. At slightly higher temperatures, the CNO cycle begins. Our sun is somewhere in between, so there's a little of both in our sun, mostly PP chain, but some CNO. And triple alpha is at much, much higher temperatures. Our sun will eventually reach that stage when it's basically going off the main sequence. Okay, I'll just give a preview of the next topic, which we'll cover mostly in next week. which is, having discussed energy production in stars, we understand that the core needs to be hot and dense. We know that the atmosphere, the photosphere that we see is less dense and less hot. How does the energy go from inside to the outside? And what determines the profiles in density, temperature, energy production, etc. in a star? We saw this diagram before showing kind of the temperature dwindling out, but and now we can kind of get a preview of the profile. Again, here we see luminosity and luminosity growing towards the outside, mass going to the outside, but temperature and density decreasing rapidly outside the area, which we will later start calling the core. And the basic equations that govern this are the two first equations of stellar structure. And they're also called the equations of hydrostatic equilibrium. So the first one you should know, this is very simple. How much mass do you accumulate with radius? Well, if you add to your star a shell at radius r and density rho of r, then the mass you've accumulated is 4 pi r squared, the surface area of that shell, multiplied by the density of mass in that shell. Alternatively, you can flip this dr to the right side and find that dm is 4 pi rho squared, rho of r dr. And I'm sure you've done similar calculations, not with mass, but with charge in first year electrostatics course. Right? If you have a charge distribution that's spherically symmetric, then the amount of charge you add at radius r is proportional to 4 pi r squared and some density, charge or mass density rho of r. Has anyone not seen an equation like this first one before? Okay. The second equation is slightly more difficult, but not very. It's the equation of hydrostatic equilibrium, which tells us, or ties us back to the beginning of our class, which is what holds all of this mass together. If the gas is hot and it has a high pressure, you'd expect the pressure to push the mass out into space. On the other hand, gravity is working to pull the outer mass in. And if you look at radius r specifically, then you can compare the pressure. We have it here. If you look at a shell at radius r and thickness dr, small thickness dr, then this shell will feel two opposite forces. It will feel pressure, net pressure pushing outwards, because pressure is large on the inside, smaller on the outside. So P at r is greater than P at r plus dr. So there's a net pressure outwards. We see that the bottom arrow is bigger than the upper arrow. On the side, it cancels out because the pressure from the left and right is in spherical symmetry equal, but the bottom pressure is greater than the upper pressure. So there's a net pressure outwards. On the other hand, there's a force coming from all the mass up to radius r. So that's what we have here. Newton's constant G times all the mass up to radius r divided by r squared to give us force per unit mass. And so we have gravitational force pulling inwards per unit mass is balanced by the difference of the pressure going up and the pressure going down. So again, if we take dr to 0, it will be the derivative dp dr. Okay, so two ways to think of this, but basically what they say is either that gravity has to compensate for the pressure gradient in terms of forces and pressure gradients, fields, or you can think of it macroscopically as having some mass, rho r times 4 pi r squared dr, feeding the gravity g m of r times that downwards, p of r divided by the same surface area minus p r plus dr on the outside. So the net pressure is outside, the net gravity is inwards, and at equilibrium, they balance each other exactly. That's hydrostatic equilibrium and spherical symmetry of the mass distribution. Those are the two first equations we're going to use for stellar structure. Any questions?
Ofer,
Yes.
the pressure is created by the fusion, right?
The pressure in typical stars is created by the heat. The heat comes from the fusion in the core. We typically distinguish between different types of pressure, which I wrote here on the left. The important ones in a star will be the gas pressure and the radiation pressure. Gas pressure is what you know from an ideal gas, K Boltzmann times T divided by basically the atomic, the average mass per atom or per particle. Particles can be either ions or electrons. And radiation pressure comes from Stefan Boltzmann's law, and it goes like T to the 4. So you can understand that deep within a star, radiation pressure might be relevant because temperature can be very hot. Towards the surface, which is what we see in the outer parts of the atmosphere of the sun, temperature goes down, and then it's really just the gas pressure that we measure. Because gas is linear with temperature, radiation is quartic in temperature. So at low temperatures on the outside, it's the gas that matters. But from then on, it's basically standard thermodynamics. We'll talk more about these equations in the tutorial. We'll talk more about them later. We'll see that these are only two of the equations governing a star. They give the mass and the pressure, but you can see that we have three variables here, three functions, m, p, and rho, and only two equations. So we'll need more equations to close the system and to really solve the star, including everything, including chemical composition, energy production, heat transfer from the core where it's produced to the outside, and we'll cover all those equations next week. Any more questions? Okay, I'm stopping the recording.